Welcome to another episode of The Edge of Science. In this episode, we are going to talk about how scientists go along by exploding stars in the simulations and figure out what happens after. Today's guest is Dr. Rahul Kashyap. He's a postdoctorate at Pennsylvania State University, and he has been working on a variety of subjects, one of them to be supernova and explosion of the stars. Glad to have you here, Rahul. How are you doing today?
Thank you very much, Reza. I'm also very glad to be here, and I'm good, going good, as good as you can do in the pandemic time.
Yeah, we are all locked in, so
yeah,
that's something everybody's expecting. So, Rahul, can you give us an overview of what have you been working on during past couple of years?
So in past couple of years, I've been mostly thinking about astrophysics of very special kind of very dense objects we call neutron stars. And not only single neutron stars, but also how two neutron stars, when they live in pair and when they merge, what kind of signal they produce, and when we detect them, how can we know about their properties, and in different windows of observations, such as electromagnetic waves and gravitational waves.
Cool. So let's jump into some basics, right? Maybe our listeners would not know what is a binary system and what is actually a neutron star. Where does it come from, right? So let's tune back the questions to what is the origin of a neutron star and how it ends up in a binary system, and what is a binary system even, right?
So there is a lot to take in. This is about like 200 years of theoretical astrophysics in development, so I have to summarize it in 5 minutes. So I will break this answer into a couple of parts. So one of the most basic thing about universe is when we look at the night sky is we see stars, and these stars are the most basic building blocks of our universe. The stars constitute to make galaxies constitute to make clusters, and all these clusters of galaxies is what our universe is. So I will describe first, how does a star is born and how it evolves, and how it ends their life, and there will be our answer to key to our question that what are neutron stars. So stars are just blobs of gas, and in particular only hydrogen gas most of the time. Uh, the all these hydrogen was formed when our universe was born, and then because they formed clumps, blobs of gas, and these clumps of gas then again, because of the reason that we are standing on the earth is gravity, and this gravity is the most powerful force in the universe, which determines the fate of all these stars and any clumps of mass anywhere. So because of the gravity, these clumps of gas starts coming towards each other and starts forming even more dense clumps. And just like when you have a balloon or a tube of cycle, when you compress it too much, it becomes heated. These blobs of gas also, when gravity pulls in, they get heated, and because of the heat, the molecules are jittering around at even higher speed. They are bumping into each other, and this bumping of molecules with each other is what we call pressure. And this gravity is trying to pull in, but the pressure is trying to put everything apart, away. And this balance is maintained at one point, and that's what we call hydrostatic equilibrium. And hydrostatic simply comes from the two words hydro and static. That means hydro means fluid, a liquid and a gas both together are called fluid, and static means at rest. So a star, what we see in the night sky, has been there for millions of years. So they are at rest, more or less. They are not flying, getting apart each other in its whole constituents. So they are more or at rest. So this rest is from is a battle between two kind of forces. One is the pressure force that is trying to pull itself, uh, put it apart, and then the gravity which is putting it inward. This balance is what it maintains it at rest. Now, when the star is born, then, before that it was just a diffuse clump of gas, and when it slowly gets compressed because of the gravity, its temperature increases. But people used this was a very big puzzle in 19th century, that people used to think that, oh yeah, when you have these gas clumps, when they get compressed, they become heated, and when something is heated, it produces light. So, and that's where all the light of the stars are coming from. But this was a very big misunderstanding. Then later we found out that that the light that is coming from the compression has to be very small, and the light that we are seeing from the stars cannot be coming from such sources. So then this was a very big puzzle, that how do stars produce their light. So then we came up with different kind of ideas, and one uh, idea was that comes from atomic physics at that time in the early 20th century, that stars are basically fusing elements together to form heavier elements, and that how energy is produced. uh, and this idea was not taken very is not accepted very readily. But then we went into that. We tested the theory. We did the observation of our sun, and then we made that theory. So the energy, uh, when the stars, these hydrogen clumps of gas, when they are compressing, the temperature increases, and at one point the zittering hydrogen nuclei, they zitter so much, their velocity becomes so large that when they collide, the two hydrogen nuclei will merge and become one helium nuclei, and they produce also energy in the form of light and other kinetic energy.
Now let's just zoom in that part when they collide. Yes. Right? In that collision, they have to surpass a threshold distance for them to fuse, right?
Yes.
So how small of a distance are we talking about?
Yeah. So this is this whole study of all these aspects has been one of the biggest adventure of physics in the late 20th century. This led to most of our modern understanding of physics. This so the even the structure of atom, what is hydrogen atom, was understood slowly by doing experiments. This was a famous experiment by Rutherford, where he bombarded a gold foil by alpha particles, which is nothing but the helium atom, helium nuclei, and then these they get scattered from the foil. And by doing this experiment, he found that only very tiny fraction of the helium nuclei were getting scattered almost opposite direction. And this helped us understand that most of space in an atom is empty, and most of the mass resides in a very tiny volume. And this is a billion times smaller than the smallest uh, bacteria that we see. And they are so small that, when you when if you consider that, if you consider a hydrogen atom as uh, a football, then the nearest electron, it will be away, kilometers away from you. So this is a very tiny volume of atom.
It is very small, and then when the threshold passes, these get fused to a new type of atom like helium, and then you get the rest as an energy. Why do we get energy? Well, so they fuse, right? So why should the energy be produced? Let me put it this way: to keep what consistent in the universe.
Yeah, this was another interesting development in modern physics, and we have to thank Einstein for that. So Einstein found that in mass of any object is also a form of energy, and so even before Einstein, people have observed some interesting phenomena like radioactivity. So people have observed that when you take certain elements, they on its own they produce light and heat, and people are wondering then what is the source of all this energy. Then and Einstein, on the other hand, he was thinking very independently about how light behaves, and how the laws of light, which is formulated by Maxwell, behave in when we look at them in a different moving with respect to each other. Two observers will look at them in a different frame, and he came up with this idea that mass is also a form of energy. So what happens in the case of fusion is when you combine two helium nuclei, it forms a helium nuclei. The mass of helium nuclei is slightly smaller than the mass of two helium nuclei.
Two hydrogen, right? I think.
Two hydrogen nuclei, yes. Sorry, thanks for correcting. And this tiny mass difference that happens goes into energy by his famous formula, E equal to mc square. And if you calculate it, it's so large that even a small mass fraction can give you very large, too large energy. So to give you an idea, 1 pound of uranium atom, when it disperses, it will give you 8 kilotons of TNT equivalent of energy. This is too much, and we found a monster in summary.
Yeah, that is how the nuclear weapons started, right? So basically, now when this fusion starts inside a star, then there's a chain reaction, right? Because the heat increases and even more velocities are introduced to the other atoms, right? And that's how the star starts being born, and there's a gigantic, sudden light coming out of it that dusts everything out around it.
So to close so we were going towards neutron star. So we still have we are halfway there. So to close the idea of star, in a hydrostatic equilibrium, I'll just finish that part. Is that so when these molecules fuse, they produce energy in the form of light, and light is nothing but particles that we call photons. And these photons, they move at the speed of light, but they also exert pressure just like any other atom. When they collide with something, they exert force on that, and then it try to move things around. And it is this pressure which maintains the star against falling itself into ever a small volume against gravity. So the pressure from light photon and the gravity, this is the battle which stars have to constantly play to maintain itself. So this is how a star is born.
One thing to just maybe our listeners to know, when the photons are coming from the core of the star, it takes a very long time for them to get to the surface of the star. I don't exactly remember the number, but it is large. For example, for sun, do you recall that number? I don't know, but it is in order of magnitude.
Yeah, I believe it was about 5,000 years.
Yeah. So the photons we see right now, it took them 5,000 years to climb up there in a way to the surface of the sun.
And it happens because the stars are gigantic objects, and mostly there is so much distance between center of the sun where most of this fusion is going on, but mostly the photons, when they start their journey from the center, it is so dense, gravity is so high that it will just, every time it will try to go into some direction, it will bump into some hydrogen atom or electrons from those hydrogen atoms and then go into other direction. And most of the time it is going, running, like a drunkard who is bumping into people in a crowd, and then the net uh, movement of it outwards is very small. And that's why it takes 5,000 years from center to come to the surface, and then 8 minutes to come from the surface to us.
Yeah,
yeah,
because
it's very interesting.
There's nothing to scatter it in the way, right? So
Yeah.
it's almost empty space. It's just traveling its way toward us.
Yeah.
So now so we know what is hydrostatic equilibrium, how the star is born. But in one point, this hydrostatic equilibrium is broken. And when the breakage happens, there's the interesting physics that comes into the game, right?
Yes. So yeah, stars are very interesting creatures, and they are also born like us, like people. They also have a life, maybe not a very good social life, but actually most of them do have social life, uh, and also they get old. Some of them, they remain old for very long time. Some of them die, but they don't die uh, you know uh, a very boring death. Death of these stars have been source of interest to humans for a very long time. So yeah, in their life, so all they have is they produce light, using hydrogen. These are all uh, produced at mostly at the center, and it's converting hydrogen to helium. So it's like, now it is like an engine. It has lots of fuel, just like a car, and it is burning those engine to produce something else like hydrogen to helium. But it can do only for some time, because it has finite amount of fuel. And not only that, it also depends how fast it is burning. If you have lots of fuel, but if you burn very fast, you are going to live very small life. uh, and this is one of the interesting fact about stars, is that the more mass you have, the more fuel you have, they burn faster and they die quickly. So this is very interesting about humans life as well. Many humans also, many creative individuals also, they burn very fast and they live very short life. So there is a very interesting analogy here.
101 correlation, right?
Yeah. So this fact of stars, that the more massive you are, the more mass you have, the faster you burn. This leads to many interesting phenomena in our universe. And you might have already guessed that this if you're burning faster, that means your life will be small. So how you are going to live your life, and how those stars will look like, that will also depend on its mass. And when we refer to this mass, we refer to its initial mass. There is a technical term for it, but I'm not going to mention it because it doesn't matter that much. So initially, when a star is formed and starts producing light, then that mass is very important when we talk about stars. And we measure all those masses in terms of our sun mass. So one equal to a star having equal mass as our sun is called one solar mass. So we divide all the stars and their fates into three important categories. One is all the stars which have mass up to 8 times, about 8 times mass of our sun, 8 times 8 solar mass. Then we have 8 to 15 solar mass, and then more than 15 solar mass. So they lie in a third category. And these three categories have different they live a different life, but most importantly, their end state is very different. So any star up to 8 times solar mass, they in their state in a very dense object of carbon and oxygen. We call them white dwarfs. Uh, the stars in the second category, from 8 to 15 solar mass, they also end their life in a very compact object. We call them neutron stars. They're just blob of neutrons. But they form those neutron stars in a very spectacular explosion we call supernovae, and that's where what you are referring to is when this hydrostatic equilibrium, this state of rest of a star, idle life ends, and then it starts exploding, and these explosions of stars, this is what we call supernovae.
So now regarding those, interesting that you said the white dwarf gets born when you are lower than 8 solar mass. We know there is a famous limit called Chandrasekhar limit, right, in physics. Now, in order, can you elaborate on that? Where is that limit coming from, and why it is important in the sense of white dwarfism?
Yeah, this has been another interesting episode in our exploration of universe. So in the early 20th century, I'll briefly describe the history of it, and because I think history of science is very important when we study science. You need not follow the historical way of understanding the topic, but you definitely need to understand how these ideas were first introduced, because that's when the time comes, you might be able to spot a mistake or some improvement in the understanding. So when we started understanding stars, as I described, that the balance of a star is maintained because of the pushing of photons from inside out and gravity pulling it inside. This balance is what we use to understand most of the stars that we see in our sky. But then some of the stars that people observed were slightly different. So to describe that, let me describe how we see stars, or any astrophysical object, to be precise. That we see all of them through light, right? This is the only source of information we have for any astrophysical object. But we don't have just light. We can also take that light and also see how that light is divided into different energy of these photons. So to describe that, I'll briefly describe that the particles of light, which we call photons, they are they come in different flavors, and we just identify them either by frequency, or you call them wavelength, or you can identify by energy. All these are equivalent categorization. So these different energy of photons, they have different kind of information that is coming from these different stars. So and in a common terms, you can simply understand it by color. So when we say wavelength, we mean color. So red, for example, has a different wavelength than the blue. So when people started observing stars, probably the first time when it happened might be million years ago, when humans started having some intelligence on Earth. They observed that the stars come in different shapes and sizes. Some are very bright, some are very faint, but they also come in different colors. Some of them are red, some of them are blue, and when the and these colors, it took us very long time to understand that the colors of these stars are also telling us the temperature of its surface. Through many important discoveries in thermodynamics, we started to understand that the color that we see is linked to the temperature, surface temperature of those stars. So for example, red is comparatively cooler than the blue stars. So to come back to the special kind of stars that people started observing, what we call white dwarfs. So they are called white dwarfs because they look white, obviously, and white simply means that their temperature is maximum. Now the puzzle was that when a star has more temperature, it is usually bigger because it is burning more fuel, so it has to produce more light. But these white dwarfs were also very small, very tiny. Their masses were also very small. So now this was a very big uh, crack in our understanding of stars, that how can it happen that a star which is very hot but it's very small. So the answer lied to the development of quantum theory in physics, which was brought by Max Planck, Einstein, Heisenberg, Schrodinger, and Dirac, and others. In this understanding, when they started the theory of matter and the quantum theory of matter, people started applying it to stars. That maybe these stars have different kinds of matter, and we don't know the full theory of it. So they started understanding and applying those theory that we have found on the Earth to those stars. And this was done by a young Indian physicist, Chandrasekhar. And he applied those theories to understand these white dwarf stars. And he came up with this surprising result that these white dwarfs are very weird objects. So he was trying to understand that if you increase the mass of these white dwarfs, so these white dwarfs with different masses, how are their radius of those white dwarfs are related to their mass. And when he found the result and he plotted it uh, against the mass on the x-axis and radius on the y-axis, he found that beyond a certain mass, radius becomes 0. And this was a very surprising result. A person who will not be bold enough or who will not trust his own result will not publish this in the current world or in any scientific time, actually. But Chandrasekhar was very sure of his result. He went on to discuss with others in England. And by the way, most of his work, this work he did on the ship when he was traveling to England from India. And so after discussing with others, he went on to the publication. People were very skeptic of it. But he went on, he described his result to many people. And the biggest criticism came from one of the biggest giant of astrophysics at that time, was Arthur Eddington.
Which was his supervisor.
Which was also his supervisor. So, and this is also a very interesting example how to fight your supervisor. Especially for scientific ideas and pursuits. So the criticism that Eddington has was, which was completely valid, by the way, that beyond a certain mass, white dwarfs radius were becoming 0. But this was absurd, right? That how can the whole mass, everything of the white dwarfs goes into a 0 volume? We still don't understand this aspect. We do see this kind of behavior in other contexts in the astrophysics, and we still don't have full understanding of this. But Eddington's objection was very valid, but the answer to Eddington's objection was quite obvious, which came few years later. The Eddington objection was that this is very absurd, and he proposed that something or the other physical processes has to come, so that when it starts collapsing, or when you put more mass on the white dwarf, and then its star radius will become smaller, then something will happen so that it will just remain at some radius, and then it will not fall further. And his insight of this idea that something has to happen so that it will not further fall was very much correct. And but on the other hand, Chandra, as people used to call him, Chandra was also correct that they cannot, be white dwarfs cannot be of all the masses. There is a maximum mass beyond which its radius will keep contracting. So how can both be right? So the idea came is that when these white dwarfs gain more mass, then because they start contracting, and we already discussed that when something, a blob of any gas or any fluid contracts, its temperature increases, and increased temperature simply means more jittering around of all the constituents, and these white dwarfs are carbon oxygen. So these carbon nuclei start moving at a faster speed, and carbon and oxygen, carbon carbon, oxygen oxygen, all these start jittering around, bumping into each other at higher and higher energies. And at some point, I think you might have already guessed that when they bump sufficiently high, they will, if you combine two carbon nuclei, so one carbon nuclei has 6 proton and 6 neutrons. If you combine two carbon nuclei, they will have 12 protons and 12 neutrons. Total mass of that will be 24 equivalent of atomic mass unit, and that is magnesium. So then we are coming to the, again, this picture of nuclear fusion playing again a role in the white dwarf. So then, so this uh, it took us very long time, another 20, 40 years, 50 years to understand this part. But yeah, so this maximum mass business, this was very interesting. So yeah.
And then I know after that, Zwicky from California Institute of Technology comes with another, mass limit for neutron stars. Basically, repeats the same thing.
Yeah. So one of the reasons that Chandra's discovery has been so significant is not because simply that he found a maximum mass for white dwarfs, but he established an important relationship that if you have uh, if you compress all these uh, elements or certain kind of particles in a very small volume, then they behave like this. So Chandra's discovery was far-fetched. Uh, Latter, so let me describe you the briefly the structure of white dwarf, like what happens in a white dwarf as opposed to normal star, so that they behave this weirdly. So when you have white dwarfs, when you compress very highly, what happens is all the electrons of these atoms of carbon and oxygen, they start they become completely free of their atoms. They were also previously free, but this time they were also compressed. So they become very much like any metal that we see on Earth, like iron bar. In an iron bar, all the nuclei of iron are arranged in a regular fashion, and the electrons are free to move. So when you connect it to a battery, the electrons start moving. And the similar kind of structure, white dwarf matter becomes, except that it's very hot. It's 10 to the power 7 Kelvin. So our room temperature is 300 Kelvin, and it's 5 order of magnitude, like billion times more hot than what we see. Sorry, million times, less than a million times, 10th of a million times hotter than our room. So in that configuration, the electrons behave very weirdly. They are very compressed, and when you compress any particle in a very small volume, their velocity becomes very large. Their momentum becomes very large, and this is the cause of the pressure that comes in the white dwarf. So instead of light acting against gravity in normal stars, in the case of white dwarfs, it is the momentum of electrons which causes this pressure. Apart from this, there is another source of pressure that comes in the case of electrons, especially. So previous source of momentum that I described is valid for any particle, but electrons are not just any particles. They are a special kind of particles who follow special properties when you combine them in large quantity. So when you look at anything in a large numbers, we call it a statistical property. So a statistical property of electrons are different than a statistical property of, for example, photons. And when Chandra discovered the limit, he was solely using this statistical property of electrons. So his understanding of maximum mass of white dwarf uh, depends upon only the statistical property of electrons. And later it turned out that, like very soon, people found out that there are other particles like electrons, and one of them is neutrons. The neutrons are also very much like electrons when you collect them in a large number. That means the discovery of maximum mass of white dwarfs immediately implies the maximum mass of anything which is form of neutrons. And we also know that you can very soon people started conjecturing that, oh, maybe if you can form a blob of atoms and where electrons are compressed and they are behaving statistically such a way that they're getting pressure, then maybe you can also do with neutrons. And as you mentioned, Zwicky was the first one to think about this and conjecture this, and his ideas were so far in the future that it took people to understand this thing sometime.
He was a kind of outlier in the physics department, not too nice to people as far as I know. So from reading from his communications with other physicists in the physics department. Now, so when we pass 8 mass, when we go higher masses, 8 solar mass, basically, when the star is big and it ends its life faster, then it ends up, as you said, core collapsing, which is the meaning is basically the gravity wins over and everything is, gravity is winning over the pressure and everything is collapsing into itself, right?
Yes.
And in that collapse is where this explosion follows, right? And let's get there, because that's the important one. Now we are getting close to the story of, right, how the neutron star is actually born, right?
So after that, like when white dwarf forms for up to 8 solar mass star, now question comes that what happens to the heavier mass star? And then, as you explained, they behave differently. So there are these 3 categories of star that I have described. So that is one way of looking at how neutron stars form. The another way of looking at is what I described earlier, is that when you take a white dwarf and you start putting more mass, then what happens? So before, I'll just briefly mention this aspect, is that the power of theoretical ideas here. That so almost same time, in Lev Landau, a famous Russian theoretical physicist, he also came up with with this idea that and he had a very back of the envelope calculation for the maximum mass limit. So he said that he was thinking about just collection of any, like, electrons or neutrons. So if you take a collection of neutrons in an object, then how much energy it should have, and if the total binding energy, so binding energy, to understand the binding energy of an object is to simply that how much energy it will take to put into it, like heat it up or hit it or perturb it, so that all the parts of some object goes to infinity. So they go to very large distance from each other. So obviously, so we in our convention, we say that an object which is stable, which is sitting at rest like a star, has a total binding energy which is negative. So if you put some energy into it, positive energy, then if you put equivalent amount of energy, then total energy will become 0. The total binding energy 0 means total energy 0 means that it is unbound. So it can it will just can remain very far from each other. So Landau, thinking along this idea, also came up with the same idea that there has to be a mass at which the total energy becomes becomes zero, and that is the limit about which you cannot go mass. So this is very interesting.
And you know that his calculations on this, Landau's calculations on this, are very approximative, not too accurate. And
but they come very close to the correct value.
So one thing about Landau is very interesting. When he was doing this series of calculations beforehand, I remember, because he was not known outside of the Soviet Union at all. So back then there were Stalin forces going around, his houses apparently. And then he had to send 2 papers, even with wrong calculations. He knew they are not very double checked, as you said, back of the envelope, to Niels Bohr, and literally mentioned to him, please publish these papers because I'm not known outside of the Soviet Union and they can just seize me from existence. So Niels Bohr had to publish these 2 papers to kind of save Landau from a possible death and disappearing. And that would be very bad for theoretical physics if that happened.
Yes. He was another giant of theoretical physics last century. No, this is very important, that this brings to the point that, like a common fraternity among physicists or scientists among different countries, that the political situation in any country is completely independent of what the the connection between scientists are. And we are still fortunate that this fraternity still exists. I'm hopeful that this will continue to exist.
Sure. So let's go back to the story now. When there are 2, as you mentioned, there are 2 ways of, because the theoretical idea is the same, that when you increase the mass upon an object which is already dense enough, that's one way. Or letting a very gigantic star, when it gets to the end of its life, to collapse everything on a small surface again. That they both have the same criteria, and the end result is, kind of very beautiful and very phenomenal.
Very phenomenal, really. Yes. So this brings to us. So this brings to us the idea of supernovae.
Yeah.
So supernova, as I described earlier very briefly, that these are the explosions of stars. So first I'll describe what is an explosion. This is not, very alien to us. We have seen explosions of different kinds. Very recently, we have seen a very unfortunate incident in Lebanon, where a cracker factory exploded. So first, I will describe briefly the physics of explosion, and then I will come to the concept of supernovae, that how it comes, and then how explosion starts in a supernova. So and then how it leads to its end state. So in explosion, what happens is, so let me really describe you a very simple experiment, like a household experiment you can do. However, children should do it under supervision. So when you take a cracker, take its gunpowder and put it on a paper, and then burn one side of it, and then you'll see that slowly it burns all the gunpowder. It will slowly burn. It will produce some light and gas, and it will do a chemical reaction and it will burst. But if you put the same amount of gunpowder in a very small volume, like compress it and bind it with paper and small strings and everything, and then you burn it, and then it explodes like boom. It makes too much noise. And so this is the difference between an explosion and what we call the other is a stable burning. So in explosion, what happens is it burns too much fuel in a very small amount of time. So this the same thing happens in a star. So as we were already talking about, is that a star is just like an engine. It has lots of fuel, hydrogen, and it's burning. but it's burning very slowly. So, and the smaller it is, it burns even more slowly, and heavier, then it burns more. And and that's where their lifetime and mass inverse relationship comes. So what happens in the case of uh, stars which is more than 8 solar mass is that these stars, when they start their life, they have mostly hydrogen. In the core, the hydrogen will burn, and then slowly it will start converting everything into helium. And then on the surface, you have little bit of hydrogen left, and most of this becomes helium. And then because since the burning, it has mostly burned hydrogen, it's not producing light anymore. And light is what it keeps it from falling. So then they start falling again, and then the temperature will again increase, and then the helium will bump into each other, and then it will produce carbon and oxygen, and uh, then the core will start forming carbon. And then you can already picture, right, the outermost shell has a hydrogen, and then there was helium, and then from the center again it starts forming carbon, oxygen. So now you have this layered onion like structure. So you have hydrogen on the top, and then helium, and then carbon, oxygen, and then this carbon, oxygen again starts forming in the again start fusing in the center, and they form magnesium, silicon, and all this on the in the shell. And in the innermost, they form again, they fuse these heavier elements, and they form iron. So this stars which is more massive than 8 solar mass stars, they have this onion like structure in their elements. So they have hydrogen, helium, and then carbon, oxygen, then magnesium, and innermost is iron. The interesting thing about this fusion process is that it stops at iron. So now what will happen once it forms iron? So iron is very dense element, and when it reaches the iron limit, then it will slowly start forming iron from the center. But when it reaches certain mass, we call we call it critical mass. And then when it reaches that mass, then it just again starts falling, because now it is not forming light, so there is no pressure to balance it from the gravity. So it starts collapsing, and then it just collapses to a very small volume. And in that process, what happens is all the electrons starts reacting with protons, and they form neutrons. So all the nuclei of all the elements, and the proton is gone. We have only neutrons, and these neutrons again get collapsed into a very small volume, and that's what we call neutron stars. To give you an idea that uh, if you have so like a very large star, like the core of these stars are very large. They contract to the radius of 10 kilometers. So its original, like the iron core of these massive stars are I don't have the figure on top of my head, but they are uh, much larger than this, and orders of magnitude. Then they suddenly collapse to form this 10-kilometer small blob of neutrons. And then you have, and then all these elements that were the layers of onions that were on the top of these uh, uh, on the top of iron, like magnesium, silicon, and then carbon, oxygen, and helium, they don't have any support, so they start falling down. And in the process of falling down, they hit the surface in the process of falling, and then that because of the compression of this, then they again feel a shock, like uh, uh, their compressed gas of all these layers, they start going outward, and this compression is so strong, then it burns. And this burning of all the layers of these stars, it happens in a very short time, and that's what we call, that's what we see as supernovae. So the full details of this mechanism is still under investigation. So people are still thinking about so that I cannot describe you fully because that's not my area of expertise. So the central object which collapsed to form this blob of neutron is still there, but it's the outer layer which all these elements are there. They fuse and form heavier elements like iron and different elements, and this burning happens in a very short time, and this is what we see as supernova. So this is one. So these neutron stars, they are born in these spectacular explosions in the universe we call supernova.
And same thing can happen if a white dwarf is in a companion star and gets mass. We'll get there, but for our listeners, when this explosion happens, since in the outer layers we have heavier elements produced, that's how you get these heavy elements in your planet, because they were shoot out to the universe, and the leftover was the neutron core.
Yes.
So that explosion is so strong, it can shoot these things to very far distances.
Yeah.
And they can go to a nebula, planetary nebula, and then when the planetary nebula is being formed, they will be fused and they'll get inside the, basically planets that you're living on, one of them Earth, that you have all of those heavy elements.
Yeah, this is one of the famous understanding or aphorisms that goes on, is like, we are made of a stardust. And this is not just metaphorical that we are saying. We are literally all the heavy elements like irons and all the elements that we see. These are formed in stars. We have not formed on Earth, all these things. These are coming from one or the star, and all of these are coming from these kind of explosions. They explode and they go to some other parts of the universe, and then we form.
So we got to neutron star from one way. The other way is, I think, the same scenario happens, but this time the surrounding material comes from another star. The hungry white dwarf is just, accreting. Which let's talk very briefly about that, because that is also very beautiful, when this happens.
So the second part of study that you mentioned is very interesting, because this connects to my work, the work that I have been involved in my graduate studies, and I'm still working on some of those aspects. And the story starts with even before, like when you have a white dwarf, and when we are discussing the conjecture of Eddington, that when these white dwarfs, then they keep increasing mass, then they start collapsing, and then something has to happen. And he was right. Yes, something does happen. And because of this, the compression, when they start falling again, the carbon nuclei start fusing and they produce elements. But the white dwarf structure is very unique in that sense. So what happens is, in the normal star, like if you have a normal blob of gas, then it's just the motion of all the elements, all the nuclei is the one that supports it against pressure. So I'm not talking about stars here. I'm just talking about any normal blob of gas. For example, our environment. In our environment, the atmosphere above the surface of the Earth, we have all the gases, right? And the Earth is pulling them down. But they have maintained their height because all the molecules of air, like oxygen and the nitrogen and mainly, and all other gases, they are bumping into each other. So they keep them from falling into the Earth's surface. So that's why we can be alive. We maintain an atmosphere. So this and this is also an hydrostatic equilibrium. Our atmosphere is maintaining hydrostatic equilibrium on the Earth's surface. So, but in the white dwarf, as I described earlier, this is not the source of their pressure, which is keeps itself from falling. But they do have those pressure. So the nuclei of carbon and oxygen, they are also moving around each other. They are also bumping into each other, and they also maintain some pressure. But that pressure is very small compared to the pressure that electron maintains, simply because of its unique property. And then so what happens in this case, when white dwarfs starts collapsing and then they start fusing, they produce energy, and because of the energy that is produced, mostly these nuclei, this carbon and oxygen nuclei and other nuclei, they are the ones who get most of the energy. They start moving around at faster and faster speed, so their pressure is increasing, but the electron pressure, which is maintaining the structure of the white dwarf, is still the same. So now you have pressure of the nuclei, which is smaller than the electron pressure, and it is slowly increasing because there is burning going on. And because and when it increases slightly, then because of the higher temperature, uh, it burns even faster, because when you burn, you produce more energy, and because of this you move at higher speed, and then your reaction rate also increases. So when it starts increasing for some time, then the whole of the white dwarf doesn't feel anything. So to give an idea, uh, to so I'll contrast it with the normal star. The normal star, like our sun, here also what happens is, in the core you have hydrogen which is burning, but uh, when it will slowly burn, and it will just fill up all the, it will use up all the hydrogen in the core, then it will start contracting again, and then helium burning will start. But this process happens almost this feedback, that you stop fusion and then it contracts, then temperature again increases, and then again it produces the pressure. This happens continuously, almost simultaneously. This feedback time is very small compared to the any information that can propagate between the from one part of the star to another. So 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 to sound or to make it more technical, in more technical terms, we say that when a hydrostatic equilibrium of a star is disturbed, it again regains its hydrostatic equilibrium in a very small time. We call that dynamical time scale. But in white dwarfs, what happens is, this electron pressure is maintaining the structure of the white dwarf, and the increase uh, pressure of the carbon and oxygen and other nuclei, their pressure is not disturbing the hydrostatic equilibrium at all for these white dwarfs. So hydro just remains there, and since its density is maintained, so increase of temperature, it doesn't fluff and so on. So it will just the reaction rate keeps on increasing, and then first it increases slowly, and then it increases very fast, and then when it reaches above the pressure of electrons, then it's already too late, and then the whole white dwarf burns in a very short time. In 1 to 2 seconds, this whole white dwarf, which is about mass of our sun, uh, or like a small fraction of it, they burn in 1 to 2 seconds, and all of this carbon oxygen burns to produce mostly iron group elements and some intermediate mass elements, and they form supernovae. So 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 this kind of supernova is called what we call type 1a supernova. So this comes from the white dwarfs, and all the supernovae comes from what we described earlier, is that more than 8 solar mass of stars. Now this here comes the another picture, that so the this picture of what when we describe that when the mass of the white dwarf slowly increases, then this reaction starts and then it will explode. This can only happen if white dwarf is, there is someone who is giving mass to white dwarf, and this comes to your question, that this white dwarf sitting alone on its own will just radiate away all energy and will not do anything. It has to have some companion star or some other source of mass which it can attract and feed upon, uh, and this in this this is the picture when these type 1 supernova happens, and these are very frequent. These are important also for distance measurement in cosmology. They are the ones using which we found that most of stuff in our universe uh, uh, is uh, is not uh, usual. according to our understanding of matter. We call them dark energy. So people try to understand that how do they form? If they are so much, how do they form? So that means most of the white dwarfs either live in this binary system. So now our question will go to the idea of what is the binary system. The binary system is simply, you know, if you have two stars, when the stars are born, and many of them are born in alone, but half the stars that we see in the sky are born in binary. So they are pretty social in that sense. So when a star is born in the binary, then depending upon the masses of these two stars, they can form different kinds of objects. So we will just focus on one particular system where one of them forms white dwarfs, another forms some other are still in the process of white dwarf, but they are not there yet. So if you have such a system, then white dwarf can get mass from the companion system, and then when it reaches its maximum mass, it can explode and form type 1a. So people have been exploring these ideas for quite 40 years, 50 years. But this scenario doesn't explain the populations of type 1a supernova that we see. So now people started thinking that maybe there are other mechanisms of forming type 1a supernova. And one of the mechanisms that has been proposed was you take two white dwarfs, and when both white dwarfs are much below their maximum mass limit, but when they go to our circle around each other, they come near to each other, and this is very interesting conclusion or result of Einstein's theory, that when you take two objects and when they circle around each other, they produce gravitational waves, and because of this they come towards each other. And so these white dwarfs, one day they will merge, and they will produce some other form of object. So this is where this question comes, that what happens, like how is there any chance that many of the type 1a supernovas forms in this scenario? So in my graduate work, I found a mechanism through which when these white dwarfs merge, they in their further evolution after merger, how it can happen that these white dwarfs, even though they are smaller than the maximum mass, they can still explode like type 1a supernova. So this is still an open puzzle. I helped understand a small part of it, that what can happen here. So this was to describe you the system of binary systems in the white dwarf. Now these systems, this can also happen that these white dwarfs, when they live in a binary system, then they can accrete mass, and when they reach maximum mass, then again they will collapse and start fusion together. But this collapse and the fusion, it may or may not happen fast, in a fast fashion always. So sometimes what happens is this fusion happens very slowly, because the mass that is increasing of this white dwarf, that is it's feeding, it's eating from the companion star, is very small. So if this happens very slowly, then this white dwarf, fate of this white dwarf is very much like a core of the massive star. Just slowly its internal parts of this white dwarf is converting into heavier elements like neon and magnesium and silicon and all this. And at one point, this is still a conjecture, that all of this white dwarf will turn into a neutron star. So all the protons of different elements will eat up electrons and form neutrons, and suddenly this whole white dwarf or an inner section or core of this white dwarf will collapse and form neutron star. And this also will be a very spectacular phenomena, but probably not as bright as others, but they will also form neutron stars. So yes, you were very right in pointing out that this and there is a another direction of white dwarfs that it can go.
Now we get to why, basically your current work on neutron stars, right? Because now we built the neutron stars, how they are, they are there, how they are formed. Now, again, neutron stars also, the interesting part is they can also go to a binary system. It's not like they can live isolate lives, right? Now, when neutron stars become binary systems, that becomes, again, interesting, right? Because they start coming toward each other because of the gravitational waves, which we don't want to get into. That's a big subject for itself. Let's just imagine they're losing energy through space-time somehow, right? They're losing this energy to the space and time in the form of gravity. And then when they come close to each other, again, another spectacular phenomena happens, which is lower energy, not as high as like a type 1a, which is very very bright. If people don't know the energy levels, just imagine sun gives us 10 to the power of 33 ergs per second. You look at it every day. Supernovas can range from 10 to the power of 40 to 10 to the power of 51 in energy, which is 20 order magnitude almost higher than our sun. So that's a lot. Like if
so a very small comparison that you can do is that a type 1 supernova that is exploding white dwarfs, it produces so much energy that our sun will produce in its entire lifetime. So that is a lot of energy, and that's why it makes it so bright and useful, because we can see it from very large distance. So it is used as distance measure.
The one idea that you mentioned, that the supernovas they're used for finding in the cosmology distance analysis, basically, because they have very consistent brightness and they're very bright. This is just for the listeners, so they can be seen from different distances. But since we know the brightness is kind of approximately the same in this phenomena, so we can know what distance are we looking at and what's going on. So this can give us cosmology. They call them the candles of the universe. That's what they named them.
This also brings me to another one of my recent work, which I really enjoyed doing. So this has been known for quite some time, since the early 90s. What you described is that the type 1a supernovae, how much the light that they produce per unit time, it increases and then it decreases. So to also give you some historical sense of the importance of supernovae, is that in the classic understanding of our universe, since Aristotle and especially in dogmatic tradition of science in Western world, it was almost imposed upon that heavens are unchanging. Most of the people used to have this belief that most of the stars that we see in our sky is just fixed there, and heavens are not going to change. But when these supernova happened, they appear as a star in some dark patch of the sky. They will remain there for 2-3 months and then they'll faint away. When this happened so bright that or nearby, so that we can see it from the naked eye, this shattered our belief that heavens are unchanging. And people are very surprised to see that, there is a new star, and they started believing that stars are also born. However, they were not very correct in thinking that it is a star as usual star, but it definitely changed our belief that heavens are unchanging, and they called it stella nova, that is new star, and that's where the name comes from, supernova.
Yeah, so actually when you say then they saw the new star being born, they were very funny ideas that somebody was putting holes into the sky from outside. So there was a fire sitting outside this sphere, so there's a supernatural being that's putting holes, one hole, so the new fire jumps in, right? But the thing is, like, yes, supernova, the first one of the very brightest one was from Crab Nebula, right? In 10,000 years ago in China, that was recorded first. That literally had shadows. People would have shadows from its light. Like
You can
that
read.
was.
You can read at night, and this was one of the brightest supernova that we that have ever happened on Earth in our, and that's because it happened in our galaxy. Yeah, it was very bright.
Yeah, and I think recently there's one of the stars that is starting to faint, right? The
Yes,
closest stars.
Betelgeuse.
Yeah, Betelgeuse. That would be spectacular if we see its explosion. That's gonna be a watch at night, because this would be very bright. It's
Yeah.
close.
This is going to be, that will become one of the biggest source of, we will be busy. Like all the scientists, observers, and theoreticians will be very busy analyzing the data and understanding it.
Yeah, already they are busy, by the way. And just for people, since they're listening to this all about supernova we are talking, there was a recent theory that 400 million years ago, there was an extinction on Earth. Lots of creatures died, right? There is a chance that multiple supernova caused that, because what happened, the ozone in the atmosphere started disappearing because of the amount of energy coming from the supernovas. And then we had, because when they were analyzing rocks, they saw UV light, a lot of UV light.
I see.
So this can be, so supernovas are pretty beautiful, but just letting everyone know, they can be extremely dangerous for any nearby solar system. So the 24 light year, you are in the dead zone. You're in a bad zone when you're close to them. 20, because of the amount of like radiation, they can cause the atmosphere to go nuts.
Yeah, this is a very interesting calculation. There has been some literature on it. People have looked at that. That simply first because of the explosion and the shock wave that it will cause, and that can have some impact. But then also you have lots of high energy particles coming out of the supernovae in form of neutrinos and other charged particles. They can penetrate the Earth. They can completely remove the atmosphere of the Earth. So yeah, I don't know the details of that, but this will be very interesting. We do have theoretical background, theoretical tools necessary to do these calculations. But
just saying, they can be very beautiful, but they can end life as we know it. They are very, very strong. They are not, and we hope nothing is close to us going supernova pretty soon. Let's just hope. Now, since we don't, in last episode, I was talking to Christine. She was studying them in a lab, basically this kind of reactions inside the accelerator. Now, in our sense, in your research particularly, you focus on simulating these explosions, because first, as we know, we haven't seen any nearby explosion yet. All we have is very far explosions in the galaxies. By the way, since I'm an observational astronomer, I've seen them exploding, how they look like. So you see a galaxy and the centroid is very bright yesterday, and today there's something brighter than it in the skirts of the galaxy, inside the arms, right? And now the point comes, this is just we seeing things and analyzing them through the data. And now we want to see them on Earth. The one way would be just to recreate reactions in a lab. That wouldn't be possible. So the best one is simulating them in a computer. That's where you've been doing most of the work, right, in your PhD and postdoc. So let's talk about that, because that's very interesting. How do you go on exploding in a star in a simulation, in a computer simulation? Yeah.
So when you explode a star in a computer, your computer doesn't explode. So that's a good thing. And the worst that can happen is, your computer will crash, or you have to install your operating system again, things like that. But even that doesn't happen most of the time. So so the idea of simulation is not new. It has been there in sciences for as long as we know. Using computers is like the way most of the physicists see computational or simulation is just an extension of our calculation that we do on paper. It's just that there are a lot of calculations that is not possible for single human or even all of the humans to do in a very short amount of time. So we use computers for that. And as long as we had, since the time we had numbers to do calculation, especially after coming decimal number system, our calculating capabilities have increased a lot, and then we can do bigger calculations in a very short amount of time. But still humans are pretty slow. And so to give you an idea, that we can do like about one calculation per second. So this is measured in flops, so like floating point operations per second. We can do about one operation per second. That is as fast as we can go. More than 60 more than about 10 operation per seconds, we perceive as almost instant, that you do something and suddenly a result comes. Our normal laptop right now can do 10 giga floating point operations per second, so 10 billions. So this is enormous, and this gives us power to do all these calculations. So where does simulation come? Simulation is nothing but we we first find the equations. So let me describe you briefly the very critical difference between research in astrophysics and other experimental physics that we do. So in other experimental physics, we observe some phenomena on Earth, and we find some law, and then we change the conditions of the experiment to check that does the observation or result of changing our some condition comes as we expected. So we use some theory to predict that this will happen, and then we change the condition, and then we see the change, and then that's how we verify that our theoretical understanding or our laws of physics is correct. In astrophysics, things are different. We cannot change the condition. We cannot go and make white dwarf slightly more massive, or change carbon. We will remove carbon and put magnesium there. These things are not possible. So we only do these thought experiments. But the good thing is that the whole universe is itself our laboratory, and there are thousands of different conditions that we can even think of. It is there already, the real universe. So if you are thinking of a star with 1 solar mass, that is our sun. If you are thinking of a star with 5 solar mass, that is also there. And so when you observe all these different stars, whatever theory you have made, you compare your observation with not just one system by changing its condition, but different systems, and that is equivalent to, or at least we think that is equivalent to, is changing conditions of experiments. So when we make our theory, so our theory for describing a star comes as a description of a fluid, which is the equations of fluid or any liquid, which is mostly governed by have been discovered by people like Euler, Navier, and Stokes, and D'Alembert, Bernoulli. These people discovered how a water flows, for example. So that we model all the stars and the gases using that equation we call Navier-Stokes equation. Apart from that, we also have to understand how nuclear reactions happen. So when you confine a fuel into a small volume, then at some density and temperature, then with time how much energy it produces, and what happens to this fuel, like from hydrogen, so it becomes what, helium, or it also burns more, and so on. And we also have to understand how gravity behaves in this condition, and that's where we use Newton's laws for gravitation. If gravity is small enough, and if gravity is very strong, such as neutron stars, we cannot rely on Newtonian understanding of gravitation. Then we use Einstein's theory there, and we also have to understand that how light behaves with matter. So if light flows through matter, it exerts pressure, and matter again takes energy away from the light, or puts more light into put more energy into the form of light. So this understanding is what we call radiation hydrodynamics. And when the light comes, automatically comes magnetic fields. So magnetic fields are the just like normal magnets that we see. these are produced because of the movement of currents in the stars, because all the nuclei and the electrons, they are free to move, so they cause some current in the stars, and they also produce magnetic field.
So for people who may not know, when you know, what does that mean when a magnetic field is coming from motion of charged particles?
Yeah.
So just imagine, you know, if you have a magnet and you have a hoop, you know, a bunch of hoops of wire, a metal wire, then you pass this through, it's going to create current. You know,
Yes.
that's exactly same thing. But in a very more complicated realm, that when you have these charged particles moving, they create magnetic fields around themselves that can be pretty nasty. It's not like those beautiful magnetic fields you've seen at school, very like circular, nice, because this is a very like fast moving environment. Since they are moving very fast, the magnetic fields are entangled. They're like tangled to each other. They're not like normal magnetic fields.
Magnetic fields make things so much complicated in the stars. That's why I mentioned it last. so to summarize, you know, like we take the equations of fluid dynamics and radiation, interaction with matter, along with nuclear reactions and gravity. These things describes most of the objects that we see. And a magnetic field which is also present everywhere, but in many cases these are very not very strong. So most of the behavior of the elements are magnetic fields do not impact that nature if they are not strong, but they also come into the picture. So yeah, and as you described, you know, like if you take a coil of wire and you connect it to a battery, it behaves like a magnet. And but these are fixed coil, and the current is moving in a fixed pattern, in a helix pattern. So they produce a magnetic field which is not changing. This is like a static. After you switch on it, in a very small amount of time, it becomes that, and then it remains that. But in real environment, in the environment, when the charge that is causing the magnetic field, they are caused by the movement of the fluid itself. These you have to this becomes entangled. So the magnetic field that impacts the motion of the fluid uh, also has to taken into account. And to give you idea of that, this also has been discovered long time ago by Ampere, that if you take a magnet and when you have a wire carrying current, so when you connect it to a battery, the moment you switch on, they get a force. So when current flows in a magnetic field, they feel a force that is described by, you know, the right hand rule that you must have seen in high school. So yeah, so these equations, so there is a set of equations that describe the states or the fluids in the stars, and we want to solve them. So we when we see stars, we can say that, oh, this is the condition that is there, and we put those conditions in our computer, and then we try to see that how it will evolve using our understanding of equations that we see on the earth, and then we compare with different situations. So and that is what we call simulation. The simulation is just that. It's just that, you know, these simulations, these equations needs to be solved very accurately in order for us to compare, and they become very complicated. So you have to be very careful in you know, in constructing those equations and putting all the necessary information into it, so that the accuracy of our results are good enough so that we can compare it against observation, and then we can say that, you know, any particular theory is really matches the observation or not. So yeah, simulations are our bread and butter.
And then when you do simulations, the thing is just people to know it's not a one-man job to sit and write all of these physics and try to simulate. It's a team of physicists, and each of them contributes to a part of this gigantic simulation codes that can become millions of lines, by the way, of programming codes. So somebody writes the fluid part, dynamics part, somebody writes the nuclear physics part that, comes from the labs in nuclear physics. Somebody writes the gravitational physics part, which is general relativity. It is very, very, very complicated itself. And all of them goes to a supercomputer. That is, if you want to count laptop hours, how much would it take for a laptop to simulate?
So yeah, there is a like, first of all, to do the simulation, we use supercomputers, as you said, and this is so the first part that you said, like, this is not a one-man job. This is very important to emphasize in a modern science, especially. Science is becoming more and more team effort than individual work that used to be, that still governs our narration of science, that a single hero of science doing all the work and other people are just following him. Perhaps the key ideas and some insights is still coming from individual people, but to do the big scale calculations and to compare it with the observation, we still rely on the team effort and all the big people. So yeah, so for example, the code that I use, Flash, this code has been developed at University of Chicago by a team of people, and not just a team of people, but a generations of teams of people. So you'll have one pool of people joining and working for 3-4 years, and then they will graduate. They will move away from there to join other faculty positions, and then other faculty positions, or they will become independent researchers, or in different discipline. Then another generation joins. So generations after generations, you develop this code, and it is important to recognize the contribution of all of them. It is very rare for a physicist to understand all the pieces of the code, and not only understand, but also understand to the level that we understand that how limited it is, that in what domains the simulation that we are doing, or this particular code that we are using, will not work. So I generally think of these big codes as as a big telescope, like a space telescope. So for an observer, like, as you must have experienced this, that if you have to observe some supernova or some other objects, you cannot go on and build your own telescope. And that also doesn't make any sense. Like you don't want to rediscover all the wheels of the that has been discovered in the past. You do want to understand those wheels that have been discovered before and their shortcomings, so that you improve their workings and provide some new tools into that. So yeah, this is I would say is very important, that that how do we approach, especially for young scientists. I have also felt this difficulty when I was starting into my graduate program, that I was torn into these two different viewpoints, that should I work completely on my own and not look at all these tools, or should I just use these tools as a black box and not understand them? But I can tell you something from my experience, is that there is a middle way between those two. You can take a tool and completely understand it, and don't rediscover all the wheels, and still and do great science with it. So this is completely possible, and this is the approach I'd suggest to take for anybody to take.
Yeah, as Leonard Susskind puts, by the way, Leonard Susskind is a famous physicist who is in Stanford University.
Yeah.
He has a very nice quote about this, that physicists are like plumbers, right? If you are a difference between a good plumber and a bad plumber is a good plumber understands his tools very well and where it's going to be used. And also a perfect plumber is a person who knows how to use these tools and make a new tool if it is needed. And there's a different type of screw.
Yeah.
So that's how, the science has become these days. And Mark Twain also puts it that it takes 1,000 men to make telegraphs, make the roads, make the, I don't know exact quote, all of these things, but we only remember the last guy. Right? So that's why, like, it's not a one-man job anymore. It's past the point. And specifically in simulations, since in the computers you do those simulations, when you mention fluids, I want to mention that very clearly. It's not a fluid that you see in the normal life or normal day. I mean, you see it. Unfortunately, yes, actually you see it. It's not like those pretty fluids you see from the fountains. These are turbulent fluids that are not behaving in a very predictable way. Like the air around you is turbulent, your blood in the veins are turbulent. Everything is turbulence. Don't get attracted to those beautiful fountains. They're not the real world. The real world is super turbulent. And that's what you guys see in your simulations there, right?
That's a whole very complicated domain of understanding of fluids, the turbulence in the fluids, and how do they impact our understanding of normal fluid or in the stars. I don't even want to go there. But to just to give a simple idea is that the equations of fluids that we solve for these stars, we have a choice in putting our equations, of course, because we are putting everything in computers for simulation. So we can choose either to put in all the real pieces of physics that we believe is there, or we can choose step by step. So if you put all the real piece of the physics, like turbulent fluid, magnetic fields, radiation, everything, it is simply not possible to solve them, even with the biggest supercomputer right now, which is available to us. It will take millions of years to do all those calculations if you just put all the equations and do the simulations. And even after that, you can always ask that, are those equations really applicable in all the domains that you are working on? So in this sense, the simulation or computational work in physics, it also becomes an art. That you art not in the sense of like producing something completely subjective. It is still objective, but art is in the sense of that you put in all the pieces of physics that you have shown theoretically that are most important for some observable. So if you're looking at if you're looking at our sun, for example, and you want to understand how much light it produces per year, then you don't have to simulate all the magnetic fields, everything. You can do very simple hydrostatic model of our star, which you can do in your laptop, and that will be very accurate. For example, neutron star mass radius relationship, that when you increase the mass of the neutron star or white dwarf, how its radius decreases, what is the relationship? This you can calculate in your laptop. So this is very simple. But so in the computational physics, you always have to ask question: what is it that you want? What is in the to compare with the observation, and how accurate you want? And this question determines that how much computation power you have to need. So if you want to do a very accurate, description of describing a type 1 supernova or some supernova light curve, you can also do that in a very approximate way, which will match its peak and some decline function. That you also do in a laptop. But if you want to do like a better calculation than that, depending upon how accurate you want, your laptop might take millions and billions of years to do that. So then we use the supercomputer to do that. So this brings back to, I'm answering your question, which is like how much simulation or power we need to do all these simulations. And this basically depends on what question you're asking and how accurate you want to be. So yeah, and this requires a very deep understanding of the physics that is involved there. One other thing I want to mention is that for some of the calculations, your laptop, like for example, when you use supercomputer, one of the normal understanding is that we are using it for speed. For example, if you put your code in your laptop, it will take million years. But if you use millions of like CPUs on supercomputer, then it will take 1 year, something like that. But for most of the programs that we use, it is not the speed that is the problem. It is the memory or RAM that we call in the laptop that is the problem. Our laptop doesn't even have that much RAM, that much data to store so that it can do calculations on those. So it is because of the RAM that we use supercomputers and distribute our calculation on different or multiple CPUs rather than speed that is. So speed and RAM both are important, but RAM is more important than speed in this case.
So now let's get to this question of when you were doing your research, basically doing simulations, all of this work, anything, what surprised you the most among the things that you've done?
Yeah. So in my small career now, I'm still very young, like not young in the sense of my mind. I'm not sure about the age, but very young physicist in learning. But in my small career, I have come up at least two surprising results that uh, I found very exciting to work on and then publish. So one of the first work that came to me is during my graduate studies. So I did my graduate studies at UMass Dartmouth with Dr. Robert Fisher, and he's very knowledgeable and amazing person to work with. And I benefited a lot with his insights into the computational power of computational thinking. So there we were thinking about the problem that we discussed some time ago, which is like how does these type of supernova form, or to put it more simply, how does white dwarf explode? So one simple picture is that when white dwarfs reach Chandrasekhar mass, it explodes. But then that picture doesn't explain the statistical property of the population of type 1 supernova that we see in the universe. So then the other picture that was put forward quite early on in the 1980s was that when these white dwarfs merge, they might produce, then the explosion condition can form in white dwarfs and then it can explode. So prior to my work, when I was working in my graduate study, people have looked into this from different perspective, and the most popular perspective at that time, or the popular result at that time, was that when you take two white dwarfs and uh, when you simulate them using a slightly different tool than I was using, still modeling as a fluid. Uh, uh, so when they come closer together, they collide, and then regardless of that how this collision starts the reactions and then how does this reaction leads to explosion, they were uh, they were putting these explosions almost by hand. So you put these white dwarfs on the grid, and then you increase the temperature artificially in your simulation, because you have freedom to do that. And then once these white dwarfs explode, then you calculate how much light comes from it as a function of time, and how these lights are distributed among different colors. So uh, the technical terms for these is like light curve and spectrum of the light. So and this was very reasonable to do so at that time, uh, because we wanted to understand that even when you take these two items in a binary system, and even though we don't understand how do they explode, but if they explode, do they really look like type 1 supernova, or they are completely different? So that part of the puzzle is still open. We still don't know whether like what pieces of simulations we are missing so that we can accurately connect the observation with our theory. But they did this exercise by artificially producing this, and then they found that yeah, it looks roughly the same, but not all the properties uh, are can be produced. So so when I was working, I looked at I started with our collaborators looking at these models, and then when they merged, so usually as I described that what happens is the smaller white dwarf is more compact, less massive white dwarf is bigger. So when they were merging, the bigger white dwarfs was getting dispersed and was forming a disk like a structure around the more massive star. And this disk and white dwarfs system, this evolves after merger. And during this evolution, I found that there is a very particular kind of physical phenomena that was happening there, which was found earlier in the context of planet formation and galaxy formation. This particular physical phenomena is called a spiral instability. This is the same phenomena which gives spiral structures in galaxies. Uh, and so this was very surprising. We found that this phenomena prior to our working, this has been found only in three contexts. One was earlier when it was discovered in the case of galaxies. Second, when people worked on it in the context of planet formation around young star. And the third was in the case of core of the massive stars, when these spiral instability were active and they were causing angular momentum transport. So they were causing mass to accrete on the central object. And then came our work where we found that the spiral instability is very active, is very important in the understanding of binary white dwarf systems. So after when binary white dwarf forms, they form a central white dwarf in a disk. And then because of the spiral instability, the mass was accreting on the central object. And when mass accretes, it causes the temperature to increase. And even though these white dwarfs are not near Chandrasekhar mass, we conjectured that this because of this mass accretion, this temperature is increased so much that these white dwarfs explode. And this is what we see in our simulations.
Nice.
But our simulations are not still not very accurate so that we can say this for certainty. So, but this is our conjecture that this phenomena is active there. And this is very important if you want to understand that how these most of the binary white dwarf systems are going to evolve in the future. Then we looked at many other mass combinations of the white dwarfs, and we found a very nice pattern that this mass accretion increases as you increase the mass ratio.
Nice.
Yeah, this is so this was very surprising for us. We looked at different and its observational properties for one of the models, and we found that there is one type on a supernova which matches really close to what we are seeing. So this was a very good, nice result. I was very happy to work on it. I'm working on some new findings, some new directions in it. So this was one surprising result. I would describe this later, the future directions of it if time comes. The next surprising result that I found was after my PhD, I went to International Center for Theoretical Sciences in Bangalore in India to work on gravitational waves and data analysis of gravitational waves to understand the properties of black holes, which comes as an interstate of third category of the stars, if you remember, which is more than 15 solar mass. So there I was working, and then in the same year when I reached there, a new kind of object was discovered, which is gravitational waves from binary neutron stars. So that you mentioned some time ago that just like binary white dwarfs, any stars can exist in binary, and depending upon their masses, they can form either binary white dwarf or binary neutron star. So when these binary neutron stars merge, they also produce light. And these lights are not as bright as type 1a supernova, that is exploding white dwarfs, but they also behave very similar to type 1a supernova. And people have been using this understanding of type 1a supernova to understand the light curve of binary neutron star mergers, which we call kilonova, for quite some time. But when I looked at their calculations, that the way they are trying to understand the light curves of kilonova, I noticed a very striking similarity between type 1a supernova light curve calculation and kilonova light curve calculation. Uh, now to now I'll briefly describe the type 1a supernova light curve special property. So the special property in type 1 supernova comes from its property of standardizability. So it's standardizable. Rather than a standard candle, we call it standardizable. The difference lies in the fact that if you take a 100-watt bulb and if you put it at different distance from you, then you will get less light per unit area. And based on the energy that you are getting or light that you are getting per unit area, you can determine how far it is, because you know the bulb, the light that is coming from is still 100 watt. So if it is coming from 1 kilometer away, you can find, you know that the original light, the energy that is totally coming out from the bulb is still 100 watt, and at some distance, you know the total surface area that it will form as a sphere. So you can find its distance. This is what we call inverse square law of the surface area. So that is what we mention as a standard candle. But in type 1 supernova are not a standard candle. Different type 1 supernova have different total energy that is coming out. So first thing that we want to find out is that what is the total energy coming out from any given type 1 supernova. So when we observe a type 1 supernova, we see its light curve, that how it increases and how it decreases. So this was a very surprising observational result from Phillips in 1990s, that he found that there is a correlation between the rate at which the light decreases in a type 1 supernova and its maximum brightness. So the rate at which a light decreases, it does not depend on distance. So now this gives you an idea, right, that if you observe some supernova and you measure how it decreases, that is independent of distance. So if you know how it decreases, and then you know the relationship between the rate of decline of light curve and its maximum brightness, then by looking at the rate of decline, you can find its maximum brightness. Once you find the maximum brightness and you know how much light you are getting per unit area here on Earth, you can find its distance. And that's what makes this type of supernova as a distance measure. So we can use it to find the distance. So while looking at the calculations of kilonova and type 1 supernova, I noticed that first I noticed that the light curves there also behave the same way. And the reason was that in type 1 supernova, most of the light, the light that comes from the type 1 supernova is coming because you have radioactive elements there, mostly nickel. Nickel decays and produces light, and that's what powers the light curve. In kilonova, you don't have one radioactive element, but you have a host of radioactive elements. But the heating that is coming out of the radioactive element, you have a fixed function. So then the idea came to me that maybe the kilonova also might be used as a standardizable candle. And so then I started looking into those calculations, and I looked at, and since we already had one observations of bi-neutron submergence and kilonova, I put all the pieces together, and surprising to me that we did see a correlation.
Nice.
So now we have proposed another distance measure in the universe, which is kilonova. And since we have now only one observation, the real test of this theory will come in the future detectors, when people will observe lots of kilonovae, they will put all the observation points in that plot, like rate of decline versus maximum brightness. Then we will see that our conjecture is true or not.
The other experiment can be that if they can see a kilonova in the same maybe galaxy that they visited type 1a before, so that can kind of see if the distance measurement is correlated between the two.
That's a very interesting idea. This is definitely something worth exploring, and I think you have already saw this idea from my head almost. So this was another surprising result which I found, and later many other groups in Caltech and in Netherlands, they have followed our research to explore different kilonova past kilonova candidate, to explore this idea. They've also come up with some independent means of finding the distance measure. But we were very happy that we are the first to announce this.
That's awesome. Congratulations. The thing is, just for listeners, why distance is important. that is what helps us to understand how our universe behaves in total, which will be itself a 2 hours, discussion why the distance is important in the universe. Now, let me ask you this, since we are getting to the end of the conversation, and hopefully you'll come back in the future for another episode, a bit more on the other side of the story, basically the universe part, rather than just the small elements. We will have that. Now, how did you got interested in science in general? What happened to you that you decided, hey, I want to become an astrophysicist, and I'm going to become an astrophysicist in the future, and specifically computational astrophysicist?
So I feel that my career path was not so much pre-planned as anyone might think, but I was definitely interested in physics from a young age, and I think looking at my surroundings, I can see any student who studies physics is interested in it. I have not found anyone who says that, oh, this is very boring. Like, everybody finds it interesting. It's just that what you choose to work on in your life can be different things, but it is interesting to anyone. So yeah, I mean, so I was just interested in physics, but growing up in India, choosing physics as your main career choice is a very risky proposition. Most of the people will say that, oh, you will end up as a tutor most of your life. And I did do tutoring for some time to get some financial backup, financial support for myself. But one of the consequences was that I had to choose an engineering discipline for my undergraduate, and I went into studying building ships and submarines. But the good thing was that I studied a lot of fluid dynamics, thermodynamics, and solid mechanics, all these processes, not to mention some very good mathematical tools like linear algebra, real analysis, partial differential equations, and all these things. So I used to study physics on my own, most of the basic understanding of as much as I could for undergraduate physics, like classical mechanics, relativity, and so on. And when I applied for the graduate program, this was very natural for me to do something which I understand. And so I choose fluid dynamics and especially computational work, because if you choose fluid dynamics and you want to understand something, the physics of it using fluid dynamics, then computational work is very natural, and I would suggest anyone to not shy away from it. So one special event in my undergraduate that influenced me towards fluid dynamics was that when I was searching for work of my project, for my undergraduate project, I was looking into different topics, and I came across this book by a fluid dynamicist, a very great fluid dynamicist, G.K. Batchelor. His book was called Homogeneous Theory of Turbulence. So by reading that book, he describes so beautifully the phenomena of turbulence in there, and he in his words, I will put as he said, I'll quote that he says that we should use like he's going to use in like I'm going to use the mathematics in this book as much as necessary to describe the essential physics, and that I found was very important as a physicist to understand that physics and math are different disciplines in think of. They are intimately related. They are not. You cannot have exclusively one mode of understanding or one mode of working, but you have to understand that what is your major mode of working, and that determines how you think and how you work. And then I went on to talk to a professor in Bangalore, Professor Javantarakiri in mechanical engineering department. He had an article in one of the magazines, so I wrote to him that I liked your article and please suggest me some references to understand more about turbulence and fluid dynamics. And he suggested me some books, and he also invited me to work on summer. So I went there to understand, to do some experiments in fluid dynamics. So I studied how clouds form in laboratory. So we used to heat up water in a small beaker, and then we used to pass this hot water through a duct, and we used to pass the cold dry air from air conditioner on the top, and we made laser sheets to understand the slices of this turbulent fluid that is going up. So those experiences brought me closer to the fluid dynamics rather than my earlier passion, which was relativity. And now in my postdoc, currently I have combined both. So now I'm studying relativistic flows and fluid dynamics in relativity. So yeah, this like just general passion about physics slowly brought me this. So there's no planned career choices here, but yeah.
That is actually one thing that we hopefully one day will have an episode about that, right? Talk about what is going wrong actually in this. That it's not, we don't have any idea when we are high school what we want to do very well. Yeah.
Yes. This requires very careful attention and lots of discussion, and we need to put pressure on the policymakers and curriculum designers who are like most of them are very remote from the current problems. So they are looking at the problems which were 10 or 20 years ago. So yeah, definitely.
We will have hopefully one talking about that. So I know that you're doing some program with Indian high school kids that you're trying to help them. Do you want to talk about that? How people right now who are listening to this hopefully podcast in India, the high school kids, how should they use that program, the program that you're offering right now?
So it's a small scale initiation that I'm exploring with my couple of friends. Still not full-fledged yet, but the basic idea is that me and my friends, we noticed that one of the biggest problem in India, and I see this almost everywhere, but in India it is more, is that there is a gap in communication. So we thought that with limited resources and everything, we are not so much capable of helping students financially or in their life about all their problems that they are facing to get good education and to come to scientific research or to do anything in their life. So we are not focusing on that part because that's simply too large a scale for us to deal with. But even for the students who are financially capable, who have access to all the education system and curriculum, they also don't end up into the profession of their liking. And the one of the problem is that we always tell in our education system, like in India, growing up in India, I always noticed that most of the teachers and curriculum system is designed in such a way that we tell students to what to think, like what topics are interesting to think about. So we say that, oh, think about engineering or think about medical or think about doing an MBA and things like that, but we don't tell how to think. And one corollary of such a system is that most of the students grow up looking for what to do and not how to enjoy whatever they are doing. So then we found that and this disconnect happens because they simply don't have the communication that whatever they want to do, so suppose a student wants to become a musician when that student is in high school, but he has no idea that how he or she can learn music first of all, And even though that student can learn music, then how actually you will go on support yourself, or livelihood based on that, your passion or the work that you're interested in, because enjoyment is not sufficient. You can enjoy doing something, but then when you are hungry, then you can't do anything else. So our job, our purpose in that program that we are doing is just to connect people who are actually in the advanced stage of that field to the people who are in a very early stage, like high school or undergraduate. And we want to just inform that like, for example, if you want to do scientific research in physics, for example, in India, you don't have to go for these competitive exams and do rote memorization and solve one problem again and again. Those are completely pointless. In fact, those are pointless no matter what you want to do. So all these competitive exams, I like completely discourage people to go for that. You especially for scientific research, what you need is a basic understanding of some topic, and then its application into new field, and then think about the new topic, because that's how we think about. That's how that's the way to scientific innovation, not the solving same problem again and again and in a very short amount of time. This makes you very fast robot, but to do a scientific innovation is not useful. So just to give an example, but when there are many disciplines like that, like if you want to do music, there is so much a struggle in to become professional musician or music director. So you have to know exactly what path to take, so that in your struggle, during the years of your struggle also, you have a basic support, and you can also do the work of your passion. So we are exploring this aspect.
That is nice. And if they want to reach you, how they can, please give me a link so I can put it in the description afterwards.
Yes, we will. Yes, so I will suggest people to watch out for this YouTube page, and then we will post our links there.
Sure. So, yeah. Sure. This is the tradition I'm introducing to this podcast. At the end of it, I usually ask a question, which is, what has been the book that you read, the first time you read that book, you just blew your mind away? What is that book in your, if you want to choose one only?
That's a difficult thing. So yeah, I don't want to choose one book, but if you insist, I would say there is a small book which contains many writings by Einstein. It's called Ideas and Opinions. And I go back to that book many times. And it's not like so much content in there, because Einstein wrote on, like, there are many different topics about which he talk about there. But he does talk about scientific research. There is a very nice article on principles of theoretical research. Then an obituary to Max Planck, that he presents there, and Lorentz, he talks about there. And then he talks about the politics and education and many different areas. And it was very insightful for me that, uh, that how he thinks about this, because in one of the places he writes that the 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 important thing about people like me is not to explore what uh, like what he suffers, or what is the actual, like, I'm just giving a summary that what is the actual state of his life, that but only how he thinks and what he thinks, or he or she thinks. So and so that is also always I'm interested in, that like that how Einstein followed the ideas that he followed, uh, and and these kind of I followed for other thinkers also. For example, Boltzmann, Rene Descartes is another one whose book influenced me a lot. His book on meditations, where he when in a very nice logical fashion he comes to his famous quote of cogito ergo sum, that I think therefore I am. That was very influential. Immanuel Kant was very I liked his book uh, on the on the future of metaphysics, where it's kind of like an introduction to all his critic books. So these books have influenced me most, I'd say. Heisenberg's Physics and Philosophy, that also was very influential on me. Dirac's book on quantum mechanics, if I'm allowed to talk about academic books, then that book, I didn't read that much of that book, but only the introduction part we just opened a new world for me, new world view of quantum mechanics, because that's when I really understood that what people are talking about in the quantum mechanics. I didn't understand what quantum mechanics, because apparently nobody does. So, but one thing I would like to say, so to summarize, answer to my question is that I would not say my favorite book, but I would definitely say my favorite publisher, and that is a famous publisher from Russia during the Cold War era. That is Mir Publisher. So all the Mir Publisher books are freely available all on Internet Archive. Anybody can go and download. And almost all of their books present whatever idea they are presenting, whether it is geology or biology or evolution or literature. I've read mostly physics and mathematics books, but also other types of books. But especially in mathematics and physics, their ideas they present in such a clarity and depth that just during the reading, very soon you will reach to the very advanced understanding of that topic in a very simple manner. There was a Mir Publisher book in my very young age which brought me to advanced topics like relativity and quantum theory. So I definitely suggest readers to read any book by Mir Publisher. If they're interested in math physics, that's there.
Sure. Afterward, I'll ask you to provide me links. I'll put them all in the description. Yes. Now, where can people find you? That's the last question of the podcast.
So I think best would be to reach me by email. I do have a Facebook account, but I'm not active there. I read that and I open it in a long time, and I also keep it deactivated for some time. Twitter, I do have Twitter handle. I'm pretty active on that, so you can reach me there.
Sure, I'll put the link there. Thank you, Rahul, for coming to this episode. I enjoyed really talking to you. Hopefully we'll get you back here for another episode later on.
Thank you very much for having me. I really enjoyed, and just to just talking there, it also helps me think about my own work a lot.
That's cool.
Thank you very much.
Thank you.
Thank you for doing this, and keep doing this. This is very important.
Thank you for the feedback, Rahul. I'll try my best.
Yeah.
Have a good day.
Have a good one. Thank you.
Bye.